Hello everyone, so welcome to Approximate Integration video series. In this video, we are going to learn why we need approximate integration. We have integration by parts, integration by substitution, and basic integration, partial fraction by decomposition, so many methods so that you can use to find integrals. But why do we need another method? Why do we need approximate integration? Well, let's learn. Let's learn it from an example. Okay, so let's try to build up to that. Let me take the example where you need to integrate x squared with respect to x. You want to find so this is an indefinite integral. So if you integrate this, you're going to get x cubed over 3, right? Using basic integration and plus c, constant of the integration. Alright, now let's think about this. Differentiation and integration has an interesting relationship, right? So if you think about x cubed over 3. Now if you differentiate x cubed over 3, you're gonna get 3x squared over 3. So 3 cancel out, right? And you're gonna get x squared. Now we already saw that if you integrate x squared, you're gonna get x cubed over 3, right? So someone can see integration and differentiation as the opposite operations, right? Like addition and subtraction, or multiplication and division, right? So that's correct. Now what we do here is that, well, we call this integration as anti-differentiation. You're reversing the differentiation process, right? You obtain x squared by differentiating x cubed over 3. Now if you want to undo, you hit the undo button. The undo button is integration. This is crucial. Now how about if this is a definite integral? That means if you want to integrate this from 2 to 5, then basically what you do is, again, you find this x cubed over 3 and you evaluate it for 2 and 5, and you subtract, right? So you get 5 cubed over 3 minus 2 cubed over 3, and if you simplify, you're gonna get 117 over 3. Okay, now there are some keywords here. One of the keywords is that x cubed over 3 is the antiderivative of x squared. Now this is very crucial. Antiderivative, I'm sure you might have heard this word. Okay, antiderivative, the name makes sense, right? You differentiate x cubed and you got x squared. So the reverse process, okay? So the antiderivative of x squared is x cubed over 3. So the x cubed over 3, we call it the antiderivative of x squared. Alright, now here's the thing. When we use integration, when we solve integral problems, we always used fundamental theorem of calculus. Okay, so what is fundamental of theorem of calculus? Well, knowingly or unknowingly, we used that. What do I mean? Think about this. Let's say you have capital F. Again, it's this cycle. So if you differentiate capital F, you're gonna get simple F. If you anti-differentiate, or if you integrate, you're gonna get, if you integrate simple F, you're gonna get back capital F. So that's what fundamental theorem of calculus is. So if you integrate simple F, you're gonna get capital F. Since this is a definite integral, you evaluate that capital F, you evaluate the antiderivative at the limits b and a, and you subtract. So that's what we did so far, right? Now think about the methods like integration by parts. Integration by parts was connected with product rule. So that's the connection between differentiation and integration. Integration by substitution, it was connected with chain rule. That's the connection with differentiation, right? So we always had a connection with differentiation. So that's crucial. Alright, so what we did all the time is we found the antiderivative when we wanted to integrate a function f. Alright, so let's learn something new then. Okay, I just wanted to review that. Let's take this interesting function e to the x squared. Now think about a way to integrate e to the x squared. Think about the method. Integration by parts, integration by substitution, or a combination of them. Give it a try. Pause the video and try to use those methods. See what's going on. The thing is that you won't be able to, you will be not able to use those methods and solve this integral. You cannot use those methods. Now why is that? Can you use basic integration? No, you cannot solve this integral using those integration techniques. Why? What's the problem? The problem here is with the antiderivative. So e to the x square, you want to find the function. So there should be some kind of a function where you differentiate it. If you differentiate it, you should get e to the x square. And you want to find that function. You want to find the antiderivative of e to the x square. So that's the goal of integration here, right? The problem here is you cannot write down the antiderivative of e to the x square in closed form or as an elementary function. Okay, now that's a lot, right? So what is this elementary function and what is closed form? So let me explain. So it's simple. So an elementary function means a functions and the functions that you see day to day, like polynomials, trigonometric functions, exponential functions, combination of them or a combination of them using basic operations. So a finite combination of these functions is called an elementary function or a closed form. Okay, so let me show you a count example. A non-elementary function or a function which does not have a closed form. So something like this. A function, so this function. Now this is not a finite combination of several functions. This is an infinite combination. I mean, if you expand this, you're going to get x plus x square over 2 plus x cube over 3. You can write this forever, right? This is an infinite combination. So the idea here is antiderivative of e to the x square could be an infinite combination of some functions. Okay, so that's the problem here. Antiderivative of e to the x square is not simple. Possibly you cannot write it down. That's the problem. Okay, so there are some functions. There are functions in this world where it's impossible to find an antiderivative. Okay, so then what can you do? Then how do you integrate them? So these are some example functions where it's impossible to find an antiderivative. Probably they don't have a closed form. Okay, probably they are a combination of infinite combination of functions. Okay, then what integration technique would you use? That's the problem. Okay, you cannot use integration by parts, substitution. What method are you going to use to solve this integral? This is where approximate integration comes into play. Approximate integration means, the idea here is that, so okay, you want to find the antiderivative of e to the x square. You want to solve this integral. You know what? I cannot do that. You cannot find the exact answer. So what I'm going to do, I'm going to estimate it. I'm not going to find the exact answer, but I'm going to estimate it. So these are definite integrals. So think about a definite integral. So you want to find, let's make it general. So let's say, let me find the space. Let's say you want to solve this integral. You want to find the antiderivative of f. I mean, this is a definite integral. Now it's going from a to b. Let's say you do not have an antiderivative as an elementary function. So what are you going to do with approximate integration is you're going to estimate, because this will give you a number, right? The definite integral, when you solve a definite integral, you get a number, right? Not a function, you get a number. So let's try to estimate it. Let's try to find a method which we can get close to that number. There will be an error, it's okay. Let's try to estimate it. So that estimation method is what's called approximate integration. Okay, all right, so that is why we need approximate integration. So hopefully that makes sense. In the next video, let's learn what is the basic idea of approximate integration. Okay, bye bye.